We used the FET simulator where we connected the battery, 2 resistors, 3 ammeters, wires, a switch, and created a circuit in which the resistors are connected in series. For the first trial, we used the resistance of 15 and 20 ohms as R sub 1 and R sub 2, respectively. For the second trial, we used 20 and 25 ohms as R sub 1 and R sub 2, respectively. And finally, for the third trial, 25 and 30 ohms as R sub 1 and R sub 2, respectively. Sequentially, we use ammeters and voltmeters to measure the currents and voltages. Our battery was set to 25 volts. We recorded our data in tablets to be analyzed.
We then used the formula R2 is equal to R1 plus R2. We calculated the total resistance in each trial. For the first trial, as shown here, adding the individual resistance, we arrive at a total of 35 ohms. For the second trial, here we arrive at 45 ohms, and lastly, for the third trial, which is resulted at 55 ohms. All of the information gathered was tailed in our table and then evaluated.
When all the devices are connected using series connections, the circuit is referred to as a series circuit. In a series circuit, each device is connected in a manner such that there is only one pathway by which charge can traverse the external circuit. Each charge passing through the loop of the external circuit will pass through each resistor in a consecutive fashion. Since there is only one pathway through the circuit, every charge encounters the resistance of every device, so adding more devices results in more overall resistance. This increased resistance serves to reduce the rate at which charge flows, which is also known as the current. Charge flows together through the external circuit at a rate that is everywhere the same. The current is no greater at one location as it is at another location. The actual amount of current varies inversely with the amount of overall resistance.
There is a clear relationship between the resistance of the individual resistors and the overall resistance of the collection of resistors. This is the concept of equivalent resistance. So the equivalent resistance of a circuit is the amount of resistance that a single resistor would need in order to equal the overall effect of the collection of resistors that are present in the circuit. So for a series circuit, the mathematical formula for computing the equivalent resistance is equal to R1 plus R2 plus R3 and so on, where R1, R2, and R3 are the resistance values of the individual resistors that are connected in series.
As observed in our data, the total resistance in a series circuit was equal to the sum of the individual resistances. This is all observed from our 3 trials. Moreover, the total current was equal to the individual currents. And finally, the total voltage was equal to the sum of the individual voltages.
Our analysis is divided into 3. First, the values of the 2 assigned resistor values are seen to be in ascending order, resulting in ascending sums through the 3 trials. This concludes that the total resistance is equal to the sum of the individual resistances. Regarding the current values, the total current was shown to be equal to the individual currents. Lastly, the voltage values, the addends seen through the trials seem to vary diversely, but all sums result in the voltage value 25, which means the total voltage is equal to the sum of the individual voltages.
Based on our gathered data, tables, discussions, observations, and analysis, we were able to verify that the total resistance of a series circuit is equal to the sum of individual resistances. Voltage applied to a series circuit is equal to the sum of the individual voltage drops. The resistor in series hold the same current. We also conclude that when connected to a voltage source and the switch is closed, the source applies a current in a circuit and series circuits divide voltages.